Unit number 3, magnetic effect of current in magnetism. The Oersted, he experimentally demonstrated this thing, that whenever a current is passing through any conductor, there will be the magnetic field around it. This thing he has done experimentally. This is the Biot-Savart's law. It gives the magnitude of the magnetic field and its direction. It is given by the small magnetic field for a current carrying coil is equal to mu naught upon 4 pi. The current I, dl is the small portion of the wire through which current is flowing, and sine theta. This theta is the angle between the current and this length, divided by r square. R square is the distance at which this magnetic field is being studied from the wire. The direction is given by the right hand thumb rule. It is a vector quantity since direction is there. The SI unit of magnetic field is Tesla. It is denoted by capital T. Here mu naught is the permeability of the free space. Permeability means how many number of magnetic lines can pass through that medium, or it is free space, so how many lines can pass through the free space. The value of mu naught upon 4 pi is equal to 10 power minus 7, and the unit is Tesla meter per ampere or Weber per ampere meter. The next is the magnetic field due to a straight current carrying conductor at any point at a distance r is given by mu naught I upon 2 pi r. Next is the magnetic field at the center of a circular current carrying conductor, and that is given by B equal to mu naught I upon 2r. If suppose that wire is having number of turns, the coil we are using n number of turns, then this expression is to be multiplied by n. So B will be given by mu naught Ni upon 2r. Here again the direction of the magnetic field will be given by the right hand thumb rule. Next is Ampere's Circuital law. According to it, the line integral of magnetic field around any closed loop in vacuum is equal to mu naught times the total current through the loop. That is the line integral of magnetic field, and it is equal to mu naught I. If there are n number of turns, then it will be again multiplied by n, then B dot dl will be mu naught Ni. The next is the magnetic field due to a straight solenoid at any point is given by B is equal to mu naught Ni, where n is the number of turns per unit length, and at the ends of the air closed solenoid. In the case of end points, it will get half, and inside the solenoid it is mu naught Ni, end points half of mu naught Ni in the case of straight solenoid. The next is the magnetic force that is experienced by a single charged particle Q that is moving with speed v in the uniform magnetic field B at any angle theta is given by force is equal to Q cross product of V and B. One more important thing is that magnetic force cannot increase the kinetic energy of the charged particle. The next point is about the trajectory or the path followed by a charged particle in the presence of magnetic field. In this side, we have taken the shape of the trajectory and what is the angle between v, velocity, and the magnetic field. The shape or the trajectory of the charged particle will be a straight line if the angle between the velocity and the magnetic component is 0 degree or 180 degree. It is circle for angle 90 degree, and it is helical for any acute angle. When the charged particle enters in magnetic field perpendicularly, then the centripetal force on it will be balanced by the magnetic force. This is the case of the cyclotron, where the velocity is given by qbr by m, and the radius is given by mv upon qb. Time period, total length over velocity 2 pi r because it is moving in a circle, and v is the velocity. Frequency is given by 1 by t. So on putting the value of r and taking its reciprocal, we get the frequency. The kinetic energy is q square b square r square upon 2m. On putting the formula, half mv square. After that, this is the important thing, that if charged particle q is accelerated by potential difference v and speed changes from say 0 to v, the work done is equal to the change in the kinetic energy according to the conservation of the energy. So the work done is given by the product charge into potential, that is equal to half mv square, and from there the velocity is equal to under root 2q potential divided by the mass. Now this is the 12th point, where the magnetic force experienced by a current carrying conductor of L length is placed in uniform magnetic field. This is given by force is equal to current into the length from where the current is flowing to the magnetic field, and this thing is can be remembered as BIL, Bill sine theta, and the direction of the force is given by the Fleming's left hand rule here. Then is the 13th point. This is about the magnetic force when passing through between the two parallel straight current carrying conductors. In this, the force is per unit length. It is given by mu naught upon 4 pi to I1 I2 by R. R is the distance that is being considered between two of them. The force between the two wires is attractive if the direction of the current is same, attractive in same, and the force is repulsive if the direction of flow of current is in opposite direction. The 14th point is about the current carrying loop that behaves like a magnetic dipole, and the dipole moment is given by M, and it is a product of current and the area. The unit is ampere meter square. Now the next point is the torque experienced by a current carrying loop placed in magnetic field is given by tau is equal to NIAB sine theta, where N is the number of turns, I is the current, A is the area, B is the magnetic field, and sine is the angle between the current and the magnetic field. And this is given by the value M cross B, where M is the magnetic dipole moment and it is equal to NIAB. Moving coil galvanometer. It is a device that is used to detect the small electric current in the circuit, and its principle is that current carrying loop placed in uniform magnetic field experiences torque. Now the current sensitivity of galvanometer is given by theta by I, and putting the value of I will get this. The restoring torque per unit twist, K here is the restoring torque per unit twist. The unit of this is radian per ampere. Voltage sensitivity, it is theta by V. V is equal to IR, that value have been put, and then I value have been kept here. The unit of this is radians per volt. Torque in galvanometer in equilibrium is when deflecting torque is equal to restoring torque, and that is given by NIBA equal to K theta, and from here we will get the value of the current, and K upon NBA is the galvanometer constant, that is given by K upon NBA. The galvanometer can be converted into ammeter. The condition is that a very low resistance, that is called shunt denoted by S, must be connected in parallel with the galvanometer, and the value of shunt is given by Ig into capital G divided by I minus Ig, where G is the resistance of the galvanometer, Ig is the current flowing through the galvanometer, and I is the total current in the circuit. The galvanometer can also be converted into voltmeter. Here in their low resistance is connected for ammeter, here the high resistance are in series with the galvanometer, which is given by R is given by V upon Ig minus G, where V is the maximum potential difference, G is the resistance of the galvanometer, and Ig is the current flowing through the galvanometer. The next is magnetism. It is the property of attraction of bits of iron, cobalt, nickel, etc. towards the ore magnetite. Magnetic field lines. These are the imaginary lines for the direction of magnetic field inside and around the magnet. The properties are the lines form continuous closed loops. They emerge from the North Pole and enter the South Pole. The tangent to the field line at a particular point gives the direction of the field at that point. This is just similar to the electric field lines, but this point is different. the electric field lines, they don't form the closed loops, but it is there in the case of magnetic field lines. And this point is same, the tangent to the field line at a particular point gives the direction of the field at that point. These lines do not intersect, that is true there also in electric field lines, they too don't intersect. Then is the magnetic dipole moment, it is denoted by M. It is a vector quantity and it is a product of the pole strength, either the north or the south pole, and the 2L is the dipole length of them. The SI unit is Ampere meter square, and this is a vector quantity. The direction is from the south pole to the north pole. Then is the Coulomb's law in magnetism. It is the product of the pole strength and inversely proportional to the distance between the poles. So this is the value of the force given in the Coulomb's law in magnetism. The magnetic field due to bar magnet at an axial point is given by mu naught 2m upon r cube. M is the magnetic dipole moment, and the direction is along the direction of the magnetic dipole moment, that is from south to north. On an equatorial point, it is given by this relation B is equal to mu naught 4 pi upon m by r cube. Here the opposite direction of magnetic dipole moment is there in equatorial point. Now the torque experienced by a bar magnet in uniform magnetic field is given by magnetic moment into the magnetic field and sine of angle between two of them. So it is the cross product of magnetic moment and the magnetic field. Now, if the magnetic needle of a magnetic moment M and moment of inertia I is suspended in uniform magnetic field strength B and is allowed to oscillate in this field, it will execute simple harmonic motion SHM, and the time period will be given by t equal to 2 pi under the root I moment of inertia divided by magnetic moment into the magnetic field. The potential energy of a magnet in a magnetic field is given by U. It is equal to the minus dot product of magnetic moment and magnetic field strength. Then is the bar magnet is equivalent to a solenoid, and the magnetic field for that is given by mu naught upon 4 pi into 2m over r cube. Magnetic flux, just as we are having the electric flux, same is the magnetic flux. The definition is also in that way only. It is a measure of, there was a measure of number of electric lines of forces, here the magnetic lines of forces passing through some surface held in the magnetic field. It is denoted by phi b, and it is the integral of the area of the magnetic field. It is a scalar quantity and the unit is Weber. Now we are talking about the elements of Earth's magnetic field. Among that, the first is the angle of declination. First, let us understand this diagram. There are the two meridians. One is the Earth's magnetic meridian and another is Earth's geographic meridian. So this is the plane that is made for the Earth's magnetic meridian, and this is for the geographical meridian that is having orange lines in that. Now, the angle between the geographical meridian and magnetic meridian is denoted by alpha, and this is the angle of declination. The angle between this Earth's magnetic field is divided or resolved into its components. This is the vertical component, this is the horizontal. Now the angle between the horizontal component and Earth's magnetic field is denoted by theta, and that is the angle of dip or magnetic inclination. So let us go by the statements. The angle of declination at any place, it is an acute angle between the magnetic meridian and geographical meridian. Alpha, it is shown in the figure. Next is the angle of dip, or it is also known as magnetic inclination. It is the angle between the direction of Earth's magnetic field, that is BE, and the horizontal in the magnetic meridian. This is BH, horizontal component. And this angle theta, it is the angle of dip. Then the horizontal component of Earth's magnetic field, it is the component of Earth's magnetic field in the horizontal direction in magnetic meridian, that is BH. Also from this we have The BH is the horizontal component of Earth's magnetic field, so it will be having the value BH is equal to BE cos theta, and vertical component is given by this. So squaring and adding, we will get the Earth's magnetic field is equal to under root BH square plus BV square, and the tan theta is given by the ratio of them. The next is neutral points. At certain points in the field, due to the magnet may be completely neutralized by the horizontal component, and these points are called the neutral points. Next is the classification of substances according to the magnetic behavior. The diamagnetic substances, these are feebly, weakly repelled by magnet when placed in magnetizing field, and they are feebly magnetized in a direction opposite to the field. And the example of such substances are copper, silver, gold. Paramagnetic substances, they are feebly attracted by magnet when placed in a magnetic field. They are feebly magnetizing in the direction of the field, and the example is aluminium, sodium, etc. Ferromagnetic substances, these are the substances that are strongly magnetized when placed in the direction of the field. Example is iron, nickel, cobalt. Then is the electromagnet. It is a temporary magnet and it is used in the hospitals where to extract iron or the steel bullets from the human body. It is used in lifting the heavy things also. So it is used in factories, used in mobile cranes to lift big machines. Permanent magnet, as the name it is indicating, they are forever and they are commercially used for making the permanent magnets for the motors and dynamos.